So then we move forward to Dr. Junior Kersten. Okay, so for robust gaming scaling control. Thanks.
Yeah, thanks. I think we've seen each other the whole day, so welcome to my talk. Anyway, I'd like to present to you some novel approach for an interval-based method for robust game scheduling controllers. And for that, I will start with our main idea, and then go on about the implementation of such. And the implementation includes the robust LMI-based control sensors and computation of the interval enclosures for all reachable states. And then I will go on about some techniques for the reduction of overestimation. And then I conclude with a short application scenario. So what is our main idea? Here are our interval representation which we used. I think this is nothing new for most of you. We use the underline for the infimum and the overline for the supermum, respectively. And the time argument in brackets, of course. So we consider a nonlinear continuous time system as such, with the state vector x and the control vector u. And we assume that the steady state operating point is set at 0, and we set the input to 0 as well, so we can use a feedback controller parameterized according to the equation below. So what we do with the nonlinear equations, first we try to reformulate that into the quasi-linear state representation, because as I already told you, we want to use LMIs, and the LMIs are just usable for quasi-linear or linear space representations. So the main idea is we want to ensure asymptotic stability for all reachable states, and that by a sequence of control matrices K, for the whole sampling time. So note that the xk plus 1 denotes the verified enclosure of all reachable states at the point of time, at the next point of time. So we assume the enclosure xk is given, and the game controller is specified for the considered prediction time interval. So our final goal is to produce or predict the next interval step, which is included in the previous one. And there we have the gain controller, which ensures asymptotic stable convergence to the desired operating point. The problem is if the new state is not included in the first one, it cannot be proven that the interval width reduces in each of the vector components. So the solution for that is the adaptation of the gain controller, of course. So to have a look at this problem graphically, we want to ensure the decrease of the interval width with every with a specified controller gain K. So, as I already said, we will achieve this with LMI-based control centers. To achieve this, we need to over-approximate this system by a polytopic uncertainty representation with parameter-dependent system. That means that we have to reformulate the system once again, so that we have the system and the input matrices dependent on the vectors of independent parameters. And this vector is then, of course, an interval, and and it includes all possible parameters. So we need to make sure that all possible independent parameters are included with all possible connections, so that we have the vertex systems with two boundings, of course, and 2 over the time of the number of the parameters. So we specify a gamma region for the desired eigenvalues, with the which is to be negative definite, and we choose this representation because it is very easy adjustable to a few gamma regions, as you will see in the following slide. So if all eigenvalues of the real-valued system of the matrix A lie within the interior of this region, there is a positive definite matrix P that fulfills the equation below. And this P is defined by the Lyapunov function. And with that, we can prove the stability of the dynamic system. So, as I said, we choose this representation of the gamma stability regions because the matrices D and D1 provide flexible possibilities for the gamma regions, so that we cannot only state, for example, an absolute stability margin, but ellipses and hyperbolas and so on as well. So, as an example, I choose the absolute stability margin. That means that for the D0 we equal 2 times gamma, and the D1 becomes just 1. So note that if there is no stability margin, if we just use pure Hubble stability, the gamma is trivially set to 0. So for the control design, we reformulate our equation from earlier to the one in the blue box. This is just the formulation for the controlled system, where we also solve this equation for the P and then get our gain, our controller gains. So note that for the robust stability for the uncertain presentation, it is necessary to determine a joint solution of Q, of course, for all the vertex matrices. And this can be done numerically by using commonly known LMI solvers. In this case, it was Sedumi for Yalma. So how did we computate our interval enclosures? Well, we see that for the piecewise constant controller gains, we need a bounding box B to be determined. And this is done by, or this is calculated by Picard iteration, where the initialized bounding box is set to the initial interval states, and yes, a new phi depending on the bounding box is calculated. So that means if the new phi is included in the bounding box, in the previous bounding box, the iteration is continued until all components of the interval diameter vector are practically identical to the interval diameters of the first bounding box. And if this is not the case, of course, the interval bounding box need to be inflated with a subsequent re-evaluation. So if we now have our bounding box, we can use the Taylor series expansion to obtain the state enclosure at the next point. And yes, this is well done with this equation. Note that the E is a discrete time error, is the error of discrete time. So now we have to do some countermeasures because we need to avoid the excessive blow-up of the interval width due to the wrapping effect that we already heard of today as well. So yeah, we need to reduce the overestimation, and Therefore, we had I will present 3 different techniques that we with that we improved our calculation. The main idea is here to represent a set of reachable states by the union of several partially overlapping interval boxes. And then the control design is performed for the convex hull of, over the complete list. So at first we need to subdivide our intervals. That means we have the list of subintervals, and the box is then the box to be subdivided is the one with the maximum volume. And the box with the maximum volume is then replaced by these 2 subintervals. Note that these 2 are just separated at the midpoint. Yeah, so we have 2 replacements, and the selection of the interval vector component, which is then to be used, is done by another evaluation of the diameter of the maximum value. And yes, well, the problem is here we get so many subdivided intervals that we need to reduce the growth of the number as well. So we need another countermeasures to apply. So one of the countermeasures is the interval merging by a convex interval hull with bounded overestimation. Therefore, we detect the candidates to be merged by this measurement, which is it's called a hull, and then we defined a limitation hull, and if this limitation is reached, then the intervals are merged. And there were earlier researchers, set the point that approximately the delta hull limit is to be set in this interval. So another reduction is a reduction by reapproximating using the disjoint subintervals. This is basically done by 2 steps. The first step is that all subintervals are replaced by 1 common interval box, and then this interval is once again subdivided into disjoint subintervals. And now we have thought about the reduction by removing the non-physical intervals. The non-physical intervals are the intervals which are not defined by the Lyapunov stability. That means we examine the Lyapunov stability where the time derivative should be lesser than minus gamma times the Lyapunov function, and then we consider, therefore we consider the controller, the known controller gain for each step, which is already given by the LMIs, and search for P, which is fulfilling our equation. So all in all, we think that the Lyapunov functions should decrease. So how do we implement that? We have, as I already said, we have already calculated the controller gains, and we used these controller gains to extract the vertex systems of the control system matrix, and then perform a consistency test running another LMI request and searching for this joint P. So note here as well, we need to take into account all the vertex matrices. So another graphically exchange. Here we have the stability region with an absolute stability margin gamma, with a positive gamma. That means that the cross-hatched area is our stability region. For our Lyapunov-based stability region, it means for the first time step, we calculate the Lyapunov stability region, and our interval box is within this region. The next time step, of course, our interval box blows up, and we have, well, the black cross-hatched box is the non-reduced box, and then we have the blue box, which is reduced by the first Lyapunov equation. But of course, this is now our next step. So we have an even smaller Lyapunov equation, which reduces our overestimation further. That can happen as well if we introduce a left-hand region, a left-hand limitation. By this time, it's chosen to be delta. And for our Lyapunov regions, it's basically the same, except that we have now a limitation in the middle as well. That means from the other side, it is limited. So now we come to our application. I think the scenario was already discussed in the earlier presentation. So yes, I will just rely on that description, and we have the nonlinear differential equations. As I already told you, we need to use the quasi-linear state space representation, so we can use the LMIs. So that means we introduce an underlying velocity control where u is the desired carriage velocity, and then we get the state space representation as such. Note that the state vector is the angle of the pendulum, the position of the carriage, the velocity of the pendulum angle, and the velocity of the carriage. So, as I told you, we need to consider the independent parameters to take into account all possible vertex matrices. And that means we introduce these two independent parameters and rewrite our system matrix as such. So the initial state, we just set the angle of the pendulum unequal to 0, and the rest of the states was set to 0. So if we have a look at the simulation results, keep in mind that we improved our simulation with every step. So I will just show you the last improvement, which was the Lyapunov-based consistency test. The wet intervals, the wet lines bound the intervals without the Lyapunov-based consistency test, and the yellow one is the with the result with the Lyapunov-based consistency test. So as you can see, it has a great influence, and yeah, we will use it further. So to conclude, I gave you a numerical verification of the new approach for an interval-based gain scheduling control design. We computed all the guaranteed bounds of all reachable states, and well, we used the LMI controller, the LMI techniques to compute the uncertainties, and then we used as well reduction of the of overestimation using different techniques. So in the future, we will have a further look at the reduction of the overestimation because, well, you couldn't see that in our presentation here, but at the end the intervals still blow up, so we have to reduce them further. And well, another idea is to take into account the worst case constraints, such as actuator limits, which would be important when we want to apply this to the temperature control of a solid oxide fuel cell stack model. So that's all for today.
Okay, interesting. Any other questions?
You mentioned the interval Taylor series based configuration. I wonder if is in your own implementation of the integrator, or are you using standard state-of-the-art tools?
We use I think you're speaking about the thing. I don't know. In a previous presentation, there was something about the difference between Picard integrals and Taylor integrals. Are you referring to that, or?
I was well. In fact, I had in mind a more general question. I think my understanding is that you are proposing ways to curb the over approximation that is obtained in the interval computations, and you show that using Lyapunov function, you can indeed reduce the over approximation. Although I have a comment there that I will give it later.
Okay.
I was wondering whether the over approximation is or is not due to your algorithm for integration. So that's
Yeah,
the question.
it's due to the yes. The interval blows up because of our Taylor series.
Okay, so it's your own implementation of the, or is it standard state of the art? I mean, because this is a well-known problem when you're dealing with interval Taylor series in high dimension, because of the rubbing effect.
Yeah, I thought it was standard. It was state of the art.
Sorry.
I thought it was state of the art.
No, is it your own implementation, or it's a software, or?
No, it's our own implementation.
Okay, so did you use the change of coordinate Lorenz method, or?
No.
Okay, so this is the main reason why you have over approximation.
Yes.
One of the reasons why you have over approximation. So maybe if you have your own implementation of these kind of techniques, or use one of the softwares available, you may have a better result.
Okay.
But I think it's interesting for you to do the implementation of the change of coordinates using Lohner's technique, and there are some references I can give you there, or use one of the several tools existing. But I understand it might be interesting for you to do the implementation.
Yeah.
Now, if you consider using Lyapunov technique to curb the over approximation, you have a strong assumption saying that the system is indeed stable for any tuning or any uncertainty. You have a kind of proof of robust stability for your system, and then you do the reachability.
Yeah.
On it.
Yeah.
So is this assumption always valid, or do you think there might be some situations where it may not?
Well, if I think it would be very difficult for systems which are not well. The problem is here we applied it to an application which is stable, which we know, and which is very easy. I think if we apply this for the SOC fuel for the fuel stacks for the stack models, it will become difficult. Yeah, of course. Because but see that the overall they are stable. We know that the system itself is basically stable, and now we have to take into account the uncertainties as well.
May I give a short comment there? And the very first stage is that you're calculating, regardless of the controller gain, a bounding box. This bounding box is being calculated with a Picard iteration, and you're computing then a controller gain that is stabilizing the system dynamics that is corresponding to this overestimated reachable set of states.
Kind of proof that the
Yes,
system is
there you
stable.
have to prove, and if the computation of the controller gain fails at the beginning, then we have to stop. Okay, and therefore we know that there exists a Lyapunov function that is proving asymptotic stability, because otherwise the very first design stage would fail.
Then what would be the use of doing reachability? I mean, let's say we know the system is stable, so what would be the use to, I do reachability myself, it's not a problem, but what would be the use of doing reachability computation if you can prove by an analytical approach that the system is stable?
Well, the problem is that we, with our first LMI implementation, we get the it wouldn't work if there is no no possible control. So we wouldn't have no solution for this implementation, and that is actually the problem to which I was referring earlier, because if the interval would get too wide, if the interval itself gets too wide, then it becomes impossible for the first LMI request to solve the equations. So in order to solve our first LMI request, we need to reduce the overestimation.
Yes, but
Sorry, I may not understand.
I have seen this, yes, I understand
And
that. That's the
the
question.
thing is, we don't want to use a constant controller gain for all times.
Okay.
We want to modify the controller gains at runtime. And the controller gains should be as less conservative as possible. And for that purpose, we are modifying the controller gain at each time step.
So when you do reachability, you do it for the closed loop system
For the closed loop system for a short period of time.
using the previous tuning of controller.
Yes.
Any other questions? Okay.